In this video we are going to talk about double Fourier series. So what is it? So first of all, let's just recall that if you have a piecewise continuous function, so let's say f of x is given and it is given to be piecewise continuous, right? Piecewise continuous and 2 pi periodic and 2 pi periodic, then we have a Fourier series representation of this function, right? Then the Fourier series is given by this. Fourier series is, so basically Fourier series of f of x is this, right? Is essentially a naught plus summation m equals to 1 to infinity a n cosine nx plus b n sin nx. And I am not writing here. You really, I hope you remember what are ans and bns. So these are basically 1 by pi integral minus pi to, so basically it is 2 pi period, right? So minus pi to pi cosine mx f of x dx, right? So those things are there, but you already know this. We are not going to talk about it. So essentially these, and here I will just write it like ans and bns are Fourier coefficients, are the Fourier coefficients of f. Yeah, Fourier coefficients of f. Yeah, and what do we know for the sake of it? See, we know that these basically the series, yeah. So these are the points we know. The series converges in the mean, okay, converges in the mean. So these we did not prove, but this of course this is a little out of the syllabus, okay, and you don't need it, but this is true. So essentially what I mean is, if you take the partial sums, yes, and so basically let's say Sn's are partial sums, so the difference between Sn and f, if you take the square and then integral, so that can be made less than epsilon for sufficiently large n, okay. So that is what it means in convergence in mean to f of x, okay, and sorry, not f of x, to f of x, okay. And of course we also, these we talked about, but again we did not prove it, that if f is differentiable, continuously differentiable C1, then the convergence is uniform. The convergence is uniform. Gens is uniform, okay. So what I meant is this. See, for a smooth function, what do I mean by smooth? As I told you in this course, on basic assumption is, whenever we say smooth function, we always mean it is at least continuously differentiable, okay. And it can, you can think of it as C infinity also, that's not a problem. So in infinitely differentiable function, but at least once differentiable, at least once, okay. It depends on the context. If you are talking about situations where we need twice continuously differentiable, we assume that the smooth functions are C2. Yeah, so that's just the way we are thinking of it, okay. So that's the idea. Now the thing is this, let's just understand it. What do we mean by double Fourier series? See, in PD what happens is, we talk about this partial derivative, right? So in PD, if you think about it, we talk about two variable functions, right? Two variables, x and y, f of x, y. And for now, let's just assume that this is continuously differentiable. Continuously differentiable, okay, right? So what does this means? It means that, see, this is a two variable function, right? So differentiable, whenever we say, we mean that the gradient of f exists, okay. That's differentiability. Yeah, wherever, at what point we are talking about, let's say this is continuously differentiable everywhere, that is what we are assuming. So the gradient exists everywhere, okay, that's what we are saying. And so when you are saying continuously differentiable, it means the derivative function, that which is the gradient in our case, we identify it with the gradient, that is continuous. I hope this is clear, okay. So essentially what we mean, continuously differentiable means the gradient exists and it's going to be continuous. And what do I mean by this gradient continuous? It means that, see, f is a two variable function here, so the gradient is essentially fx and fy, right? So basically this says that both f of x and f of y exists Okay, so both partial derivatives exist and is continuous. Okay, so that is what we mean by continuously differentiable in this context. Okay, so we are given this function and we are going to assume another thing. See, let's say that it is a periodic function. Okay, so a small definition, let me put it as a small definition. If from R2 to R2 to R is called 2 pi periodic, is called 2 pi periodic. Okay, see, this is just a definition. I mean, please don't think read too much into it. This is just we are defining something like this. So essentially what we are saying is a function from R2 to R, when is it 2 pi periodic? If this happens, f of xy at any point, f of xy, if the functional value, if you fix a y, the f should be periodic with respect to x, 2 pi periodic. Okay, so this should be true, and again if we fix x, it should be 2 pi periodic with respect to y, so it is x y plus 2 pi. I hope this is very clear. This is very easy. Yes, so essentially let's just draw a small picture and understand what's happening. See, let's say this point is x and y, right, and so this is your x, that's your y, right, x axis, y axis. Okay, now let's say this is x plus 2 pi, yeah, and let's say this is y plus 2 pi. This is just I'm assuming it, nothing special here. So this is x y plus 2 pi, this point, and then that point is x plus 2 pi, and then you have y. Okay, so what I am saying is this, the function is 2 pi periodic if given any point x y. So this should hold for all x y in whatever domain it is. So in our case, let's say it is in R2, so for any point in R2 it should be true. Okay, so see, the thing is this, what I am trying to say is this, the functional value at the point x y should be equals to the functional value at the point x plus 2 pi y. Again, it should also be equals to the functional value of f at the point x y plus 2 pi. Is it okay? Right. So as an example, it is very easy to construct an example of it. So let's say if I am taking a function c, f of x y, to be sine x and cosine y, let's say cosine y or cosine x sine y, doesn't matter. Okay, so both are periodic functions. One is a periodic function in x, one is a periodic function in y. You can easily check that the above is true. It is easy to check that is 2 pi periodic. Yeah. Why? Because you see, once you fix a y, this is basically looks like a constant, and then this is 2 pi periodic. And again, if you fix a x, then this is the only function which is talking about, which we are talking about, which is again 2 pi periodic. So basically this is true. Okay, so this is the sort of function which we are talking about. This is 2 pi periodic function when we are talking in the context of several variables. Okay, let me put another question. Find another 2 pi periodic function, Okay, of course constants are always 2 pi periodic, that you don't have to do all that, but we are definitely not really interested in those constants. Anyways, so I hope you have an idea of what 2 pi periodic functions now. Now with that said, what we want to do is we want to find out, let's say given a function like this in PDE, what happens is we always talk about several variable functions, right? So we need to know if we can find out Fourier series. If such a function, let's say if I give you such a function, can you find a Fourier series out of it? Okay, so what we can do is see, and this is very easy actually. So what we do is, first of all, so this is finding the Fourier series, finding Fourier series of f of xy. So again, I am doing this thing in 2 variables. You do realize everything, whatever I am doing, that holds for several variables also. So basically 3, 4, 5, you just increase one more variable here and the exact same thing holds. So 2 pi periodicity formula and everything else holds. Okay, right. So we are just looking for, now we are just doing it for double Fourier series. You can do it for triple, and you can do it for 4 times Fourier series. Okay, so all of that can be done. So what's the idea? Let's just understand the idea, you can get the rest of it. Okay, first of all, you fix a y. Okay, fix a y. So of course y is in R. So once we fix a y in R, you see f of xy, it becomes a one-dimensional function, right? So you see f of xy is uniform, I mean, it's a one dimensional function. You understand what I'm saying, right? See, it's a two variable function x and y. Once we fix y, then f is just a function of x. Yes, and of course, since f of x y, we are going to assume that, see, this is continuously differentiable. We are assuming, okay. So f of x y is 2 pi periodic and continuously 2 pi periodic and continuously differentiable, and c1. Okay, so if we fix a y, so let's say that will be our phi y of x. We can define it like this, which is f of xy. Okay, so this function is just a function of x. Okay, this is how we write. This is the definition. Okay, this means definition. Okay, so now this function is again 2 pi periodic with respect to x. Yeah, you can easily see that with I mean, if you look at the definition. And of course, again, it is c1 with respect to x. Okay, so with respect to x. Now for this sort of function, we know that the Fourier series exists. So what should that look like? So phi y of x, let's say, which is by definition f of x y, and that Fourier series will look like this. Yes, a naught of see, you remember, right? Let's say that I'm given this function. Let's say f of x is given. Yeah, f of x is given. That will be written like a naught plus summation a n cosine nx plus b n sin nx, right? See here, a n's, b n's, a naught, these are constants, right? Now if I do, I mean, now this is just a function of one variable. Now if I want to put it here, this a naught which I am writing, this should depend on y, you see, because this is for one fixed y. So if I mean running y, that a naught will change according to y. So a naught is a function of y in this case, so we will write it like this. Yes, plus summation n equals to 1 to infinity. Now you see this a n, again a n, this will be again a function of y, not a function of x, remember, because we are talking about the Fourier series with respect to x. So a n y cosine n x, yes, plus b n y. See here, please understand this thing. Cosine nx, sin nx, this is because of the expansion with respect to x, right? Now these constants generally, for any fixed y, this is just a constant. But the thing is, if y is varying, then f of xy has to be written like this. Yes, I hope you understand what's happening here. See, if you fix a y, let's say y equals to something, yes, I don't care, maybe 1. Yeah, so in that case, this function is basically a one variable function. It will look like this. And then this variable is basically a naught at the point 1, so basically some constant, and this is also constant, this is also constant. That's our original Fourier series. Okay, so we are modifying it like this because that x and y part is there. I hope this is clear. Okay, so one thing, let me just put it correctly. Okay, now you see, what about the coefficients? If you remember the coefficients, so where the coefficients where a n of y, that coefficient is what? It is 1 by pi. See, it only depends on x, right, in this case. So basically minus pi to pi. This is for a fixed y, right? This is for a fixed y. I have fixed a y. So it is just on x, f of xy cosine, nx dx. nx dx. Okay. And of course you have bn of y, which is 1 by pi minus pi to pi f of xy sin nx dx. Yes, okay. So with that being said, one second, yes, I hope this is clear, everything is fine. Okay, now see these coefficients, if you look at, see this function f is continuously differentiable with respect to y also. It is continuously differentiable with respect to x and with respect to y. So this is continuously differentiable with respect to y. Cosine is also definitely continuously differentiable. Yes. So you see these coefficients a n and b n, if you think about it, so these are c1 with respect to y. Note. Yeah. See these are functions, right? These are functions. And as y changes, the value changes. So essentially what I'm trying to say is this: if you look at these functions, these are very very nice functions, basically integral functions, and you can show that they are continuously differentiable with respect to what? With respect to y. So here this y is only changing. This is just a constant in this case. Okay, I mean you can think of it like this. Okay, so with respect to x, and so what we can do is we can actually expand them. Yes. Okay, so then what we can do is this. So these are I mean C1 function with respect to y. So we can write it as this: a(n) of y is a(m)n, okay, plus summation. There are two variables, so you have to be a little careful of what you are writing. M equals to 1 to infinity a(m)n cosine n sorry my, yes, m y plus, so please keep in mind which is m, which is n. Yes, see here a n is the function. Yeah, think of it like some phi of y. Okay, so n is fixed. It is with respect to the summation is with respect to n, so that is why this n is there, plus b m n and then sine m y. Okay, so that's your I mean the Fourier series. What am I doing again? See, this is a new function, right? A n y and b n y, these are two new functions, and they are continuously differentiable with respect to y. Of course, you do realize that they are going to be periodic also because of the definition, because f is going to be 2pi periodic, this is 2pi periodic, right? A n y. So we can talk about Fourier series. So the Fourier series of a n y is given like this, and similarly the Fourier series of b n y can also be written as I should write it as bmn, right? Let's just do it like, okay, nah, I should not write. You see, that's the thing. We should be very careful here. Yes. You see, these bmn and these bns has nothing to do with each other. Okay, they are totally different. Okay, so b and y, the coefficients, we have to write it like this: c. Okay, one second. I made a small mistake here. This should be 0, which one variable should be 0. See, a n is fixed. Yeah, m is 0, and then m equals to 1 to infinity. So m equals to 0. This is the term, and then the remaining term m equals to 1 to infinity is this. Okay, so b and y can be written as c n0 plus summation m equals to 1 to infinity. Yeah, again, when you do this double Fourier series, I am telling you, be very I mean, you know, vigilant, because otherwise it may, I mean, because there are variables involved here. So it is c m n, the Fourier coefficient I am writing in terms of c, Fourier coefficient of this function b n. Okay, and then you have cosine my plus dmn, okay, sine my. I hope this is clear. Okay, now where, let me put down what the coefficients are. Amn equals to 1 by c. Amn, this is 1 by pi was already there, right? And then you have another 1 by pi. So basically it becomes 1 by pi square. 1 by pi square minus pi to pi. Again minus pi to pi f of xy cosine nx cosine my dx dy. I hope this is okay. Yeah. So these are this coefficients amn, bmn, dmn, cmn. These are the coefficients which I am writing here. Okay. Okay. What about bmn? Bmn is 1 by pi square minus pi to pi minus pi to pi f of xy. Okay, one second, let us check. Bmn, right? So it will be 1 by pi minus pi to pi. Then you have another 1 by pi here, right? Okay. This is sine n y, right? Sine n y. Okay. So this is cosine nx sine ny dx dy. Okay. So the cosine part is already there. Huh? See n-a-n-y, this cosine part is already there. So I just have to figure out what this b is with respect to sine. So that sine part I am just writing. Okay. So with the cosine thing, this is just the sine, and a is that first coefficient, that is cosine. So that is why it is cosine. Okay. So I should write this first and that later, but anyways, I mean it's okay. Cosine nx, yeah, one second, this should be sine m y. So this is what I'm saying. Yeah, there are two variables m and this thing, two things m and y, right? So you have to be very careful about it. See, think about it. What is bmn? If you think about it, this particular coefficient bmn. So this is the Fourier coefficient with respect to the sine thing. So it will be integral of that sine part will be there, right? So that's what I am writing here. Okay. Similarly, what is CMN? CMN, we don't have to look at it. It is essentially the same sort of thing. Minus pi to pi, and then f of xy sine of nx cosine of my dx dy. Okay, and dmn is 1 by pi square minus pi to pi minus pi to pi f of xy. Okay, and then sine nx is already there. Yeah, and I just have to change this thing as sine my dx dy. Okay, so you see these coefficients a and y already has this thing, and then I have this bmn corresponding to that part is there. So I have to put everything together to get the original coefficients. So I hope this is clear now. Okay, so now if we substitute all this in our equation, yeah, what do we get? Which equation? This equation. Where is it? We wrote it somewhere, no? This equation. Let's say call it 1. So if we put everything together in 1, what do we get? Therefore, f of xy can be written as a 0 0, m equals to 0, n equals to 0 0 0, right, plus summation m equals to 1 to infinity. Okay, a 0 m cosine my plus b 0 m sine my. Okay, plus again summation m equals to 1 to infinity. This is a n0 cosine nx plus one second, a and then c, right? C n0 sine nx. I hope I am doing it correctly. It should be something like this. Yes, plus you have the double summation now. So this is m equals to 1 to infinity, n equals to 1 to infinity, and then you have this a n m cosine. So this should be a n m. I wrote it like this should be a n m. This also should be b n m, something like this. This should be d n m. This should be c m n. But I mean, it doesn't matter. You can write it like this. So it's not a. It's just a notation in this case. So it's not an issue. So let me write it this way: cosine nx cosine my plus b mn cosine nx sine my, right? Okay, plus c mn sine nx cosine my plus d, it's a little complicated, huh? So please bear with me here, sine of nx sine of my. Yeah, so this is the whole thing down. So this is called the double Fourier series, double Fourier series of f of xy. Okay, now you see there are some corollaries which we need to understand here. So some remarks, remarks. Okay, see